Okay, today we're going to be going over a machine that does not turn on. You have no light on the charger. This is with a known good DC inboard and known good DC inboard cable. So we're going to go over why that is. So the first thing that you should check is the one-wire circuit. I've gone over this in previous videos, but I'm going to go over it in this one as well because, might as well. Makes it easy to understand. So if I were to flip over to the screen capture, the reason I'm really talking really low today is because I got my earwax removed, and I was supposed to do that about 4 years ago, and now everything is just incredibly loud all the time. It's driving me crazy. So I'm talking very low because I hear the S's and everything. I can hear the air moving inside. Like, usually you could just hear the air conditioner, but I can actually hear the air moving inside of that duct. The things that I can hear right now are just amazing. So anyway, the way the one-wire circuit works is very simple. You have this adapter sense line that's coming from the charger, and that's going to go to this chip over here. This chip is going to allow the adapter sense line from the charger, which is where the charger talks, to talk to the SMC. See, this is the SMC over here, and this is on the sys one-wire line. Now, this chip is going to turn on and let them talk if it has 3.4 volts at the VCC pin. The VCC pin is kind of like the power pin. For example, with my microscope camera, it has this little 5-volt plug that turns it on. This is the VCC pin of my microscope camera. So back here, this logic gate is going to let this turn on if SMC, BC, ACOK is present. So if SMC, BC, ACOK is present and PP3V42_G3 hot are present, then this logic gate is supposed to send 3 volts over to this. Now, what makes the Air a little bit more confusing is that the one-wire circuit on the MacBook Air is not on the motherboard, it's on the DC inboard. And it looks very, very similar to what it looked like in some of the older models. So let me just take a look over here and get it under the microscope for you so that you can see it. There we go. So that is the one-wire circuit. See? It's all pretty. That is the one-wire circuit. So what I'm going to do over here is I'm just going to check and see that SMC, BC, ACOK is present, and also that PP3V42 are present on this motherboard. So I'm going to go back over to the screen capture over here. We're going to check, use the nets feature of this program, SMC, BC, ACOK, and we're going to look for it, and let's see where I can measure it. So I can measure it on the third resistor down over here, so we're going to find on the motherboard, and let's see what I have over here. When I measure, I see 3.3 volts on the multimeter. Let's see if you can even see that. Can you see the No, you can't. Oh well. You'll just have to trust me that it's 3.3 volts. And in order for that to be 3.3 volts, PP3V42 has to be present because PP3V42 is the power line that is pulling up the SMC, BC, ACOK signal. So what do we do next? Now, if that's working, that means that this IC is most likely getting power over here. This U6900 is. And I am using a known good DC inboard, so I don't have to worry about that. And what could be next? Well, the SMC. Let's check over here. So what's going to turn on the SMC? So we're going to look at the SMC chip. SMC. What turns on the SMC is going to be something called SMC_reset_L. Now the way this works is this chip is how do I describe it? I'd say it's kind of like a brownout detector. So the whole idea here is PP3V42 powers the SMC. That is the rail that powers the SMC. However, it takes about a little bit of time for that rail to become exactly 3.42 volts. If the SMC attempts to start before that rail becomes the exact 3.42 volts it's supposed to be, the SMC will crash and stop working and nasty things will happen. So what happens is that this chip waits until PP3V42_G3 hot is stable, and then it releases the SMC reset signal, which will then let the SMC turn on. By release, I mean that it goes high. So SMC_reset_L. This means reset the SMC when the signal is low. So when that signal is low, like 0.5 volts or 0 volts, the SMC is in reset mode, which is kind of like a desktop computer. If you have a desktop computer and you try holding down the reset button, when you hold down the reset button, you'll notice that the machine, even though it's on, is not doing anything. So try this if you have an old desktop, because I know a lot of new machines don't even have a reset button anymore. If you just hold the reset button and you keep it pressed for like 10 seconds, the screen goes black, it doesn't post, it doesn't beep, it's on, the fans are spinning, but it's not doing anything. Same thing is present over here. So the way this is going to work is it's going to reset the SMC. Now, there are a couple of ways that SMC reset L can be lowered. This chip can be dead. If this chip is dead, it will lower this by, let's say this chip dies, ground and reset will become tied together inside the chip. SMC manual reset underscore L. The manual reset could be triggered by lowering this. Remember, underscore L means when the signal is low. If this capacitor breaks, which happens very often with people's fingernails, remember when a capacitor dies, it often turns itself into a wire. So this is your capacitor. Now when it gets damaged, it turns into something like this. So now over here you have something that is not going to pass DC. It's going to go and fail. Whereas here you have something that will pass DC just fine. So when a capacitor fails, it often shorts. And if this shorts, that can happen. So let's take a little look at what's going on in this area. So if I take a look at SMC manual reset, and I actually have memorized where this shit is on the board at this point because I've checked it so many damn times. Let's see if I... Okay, we do this. 2.7, that's good. And then we check over here, an SMC, which pin am I even checking? Am I checking the right pin? Let's see, what does the board view say? Board view says, okay, so SMC manual reset is up here, and that is 2.7. And then SMC reset is up there. Okay, I was checking the wrong one. So SMC manual reset is high, that's good. But SMC reset is 0.5 volts. And there are a couple of things that could be causing that to be low. SMC reset L can be low because this chip is bad, or it could be low because the SMC itself is bad and then pulling the signal down. So if you look at the pathways that SMC reset L has to ground, actually there's a couple of different things. This signal is pulled up by PP3V42 by this resistor. So this resistor over here is going to pull SMC reset L up to 3.42 volts. So I can always check R5100, and let's just see which one over here is R50. R5100 is on the other side of the board. Go fucking figure. Of course it is. And so R5100 is here. I can measure this. I can make sure that there's voltage present over there. But there's always voltage present over there. That's never the issue. The pull-up resistor is almost never the issue in my experience. So we're just gonna check it just for thoroughness. So I get 3.4 volts there, and I get 0.5 volts there, and the resistance of that pull-up resistor, let's see, what do you get me? $51.23 kilo ohms. It's good enough. I'm not looking. A lot of people say, why are you measuring the resistance of a capacitor or resistor in circuit? It's not going to be accurate. I don't care. I need it to be good enough. If that resistor shows me OL or millions of ohms, bad. If it shows me 100 kilo ohms or under, 50, it's fine. Because I want you to think about this. If this resistor over here, R5100 or 50 kilo ohms instead of 100, why would that matter? I should still see, if anything, if it's 50 kilo ohms, there should be a higher chance of me seeing voltage over here than 100. So I don't really care. As long as that's in the ballpark and I know what the circuit is supposed to be doing, I'm fine. So I know that the purpose of this resistor is to pull the signal up. So the chip could give it a path to ground, or whatever else is on that line. So this chip could be giving it a path to ground. This connector could be screwed up and giving it a path to ground. You never know. Let's take a look at what the connector looks like. So J6100 is this thing over here. Believe it or not, that connector gets screwed up more often than you could think. And it looks like I've already taken it off because I'm used to that connector screwing things up. So the connector is not even... Actually, wait. We have 2 points over here that look bridged. Did I take this off or what? Huh. So we have 2 points over here that look bridged. And the points that look bridged... Well, I'll be damned. Those points that look bridged are for SMC reset. Do you see that? Check that out. Do you see that? I'll keep zooming just in case you can't see that. Look at that. Whoa. Okay. Am I going to fix this board by pressing my soldering iron to the table? Okay, let's take a look here. Am I going to fix my board? Just take a look. See, SMC reset is this pin, pin 12, and then SPI something or other is there. So let's take a look. Well, is this what the thing was all along? Because I usually remove that connector and I go over it. Now I am going to plug it in, and if this turns on, this would be... Okay, so it's not turning on, but I got a light. You see that? I didn't have a light before. Okay, so problem number 1 solved. I don't know if I turned this off, took this off, because I have a feeling that if I took that connector off, that there would be flux all over the place. Because I don't ultrasonic these boards until I'm done with them now. So I don't... I want to say that I did that, but I don't feel like I did. Either way, we have a green light. That's pretty cool. All right, so we have a green light, so now we have to move on to why the fan doesn't spin. So we're going to go and check the rest of the rails on this machine. Now, what does SPI Alt IO3 hold L whatever go to? So let's check this out, because keep in mind that something was trying to supply 3.4 volts directly to what that is. So that's pin 10 of this connector. Pin 10 of this connector is this. So where does this go? SPI Alt hold, that's going to go to SPI IO3R, IO3, which is going to go here. And that is going to go directly to the CPU. Ooh. I mean, just out of curiosity, what is that usually? What does that usually measure? What voltage is that used to seeing? Oh, Jesus. Oh, that was... Okay, that is 3.3. Okay, so I don't think sending 3.3 there would particularly do anything. The reason I don't think it would do anything is because it's 3.3 already. Okay, so this kind of brings us to a standstill. Let's check around the BIOS chip, because that's the only hint that I have at the moment that anything was going on. So that SPI, MISO, SPI MOSI, SPI clock, and all this crap over here, this is usually related to the SPI ROM. Also, I guess if you're used to dealing with PCs, the BIOS chip. So let's take a look around U6100 over here. So if we look at U6100, we look over here, and this is the BIOS chip, or SPI ROM chip, because SPI, I don't know, SPI ROM just sounds pretentious to me for some reason. I know it's silly to say that out loud, but it just does. So if we look at the SPI ROM chip, what do you think here? Should we reflash the BIOS? Should we reflash the BIOS? Should we reflash the BIOS? Does anybody have a clean BIOS? Okay, the reason I'm saying that over and over again for those of you who are not regulars of the channel is because there are many forums out there where people will just jump to flashing BIOS and asking for a BIOS if they have anything related to a BIOS problem, rather than actually look... I mean, SPI ROM. They will look for the SPI ROM if they suspect they have an SPI ROM problem. Where this is where looking really comes in handy. What the fuck is this? Look at that. Fuck you. Get off my board. All that shit can GTFO. So I don't know what that's for. I'm going to take a wild guess that is a terminator resistor between the BIOS and the CPU, or the BIOS and something else. I mean the SPI ROM. How dare you call it a BIOS? That is not a PC. It is an SPI ROM. I guess this is what they're talking about when the Apple lobbyists say that I'm turning a Mac into a PC. Because I'm putting a BIOS on it, when it's supposed to be an SPI ROM. The lobbyists are right, man. I really do turn Macs into PCs. I do turn Macs into PCs when I fix them, and then I misrepresent them to my customers. I'm an asshole. I'm a grade A asshole. Yeah, I'm not touching that BIOS. Fuck that. Cleaning EMI region, no thank you. Making EMI regions, no thank you. That's a lot of pain in the ass that I don't feel like doing. And it's not even going to fix it. That's the thing, you could do all that shit and you're not even going to fucking fix it. Because the problem was something else. And all you had to do was open your eyes and look at it. Just look at it. If I get anything done with this channel, if I get anything done at all, I want you to look at shit. Just look at it and guess. Sometimes I have students come and I'll go, what do you think this does? And they'll go, I don't know. And I go, guess. And they go, I can't guess. What do you mean you can't guess? You can always guess. You can always get a guess wrong, but don't tell me you can't guess. And I'll tell them, there is no consequence to getting the answer to this question wrong. The only negative consequence will occur if you can't guess. I need to know that when you look at something that you have the ability to come up with educated guesses. Jumping to conclusions is what this is all based on. And I'm jumping to the conclusion that this is going to work just fine once I'm done with everything that I'm doing here. Now keep in mind, I'm not going above and beyond to make each joint very pretty. All I did is I just put solder on each pad, using the old flux to keep stuff sticking around. And then when I'm close to done, what I'm going to do is I'm going to melt them all in nicely. The thing is, I don't want to spend too much time with hot air on each individual component, because since these components are so close together, I'm going to be hot airing each one each time I do this. So what I want to do is do one hot air at the end with flux to flow them all into place. This is why the donor board thing is amazing. You get these factory reject donor boards that had never had liquid damage. They had a bad CPU or a bad internal V or something like that. It makes everything just so efficient. Okay, this. Watch all those resistors. Watch. Okay, bam. They're in place. A little crooked, but what are you going to do? Hey, look at this board. The stuff on this donor board is perfect. People are like, how dare you take a resistor off of a donor board? Look at this. This is beautiful. This is beautiful. This is a lovely board to take stuff off of. Hey, like, am I going to take that? No. That? Maybe not, but, you know. I'm probably going to avoid this area. You know, But they're a really excellent and efficient way to troubleshoot these things. So now I'm going to plug this in. I'm going to wait for my fan to spin. My fan don't want to spin. Alright, so let's keep chasing down the path that we were on. So I put a lot of things back in this general area. I don't want to go too far off the reservation here, because I genuinely feel like this is the area the liquid got to, and this is where my trouble is going to be. So what are you, Mr. Resistor, with your white cap ripped off? Let's also take a moment to check out what power rails are actually present before I go resistor hunting. So I'm going to fast forward and see if I'm in an SO state. So I'm going to plug this in. Because keep in mind, if I'm in an SO state, then I know I can ignore all the S3 and S4 and under it power rails. I'm going to take my multimeter here and try to put it where you can see it, which is... This is not going to work, but I'll just read out the voltages as I go. We're going to go to page 61 on the schematic. Okay, so let's see where PP5VSO shows up. I know it's on the fan connector, but I always forget which pin of the damn fan. Here we go. Okay, so let's see. If that's there, then I know that I'm getting somewhere. So I have PP5 ESO, so I'm actually in an SO state right now. Now let me explain why that's important. Let me explain why this is something that that should be to you in troubleshooting. Now, there are different power states in the machine. There's SO, which is on. There's S3, which I believe is sleeping. There's S4, which I believe is hibernating. There's S5, which I think is off, but battery plugged in. You should double check those because I could be wrong. So please Google and figure out what those mean for yourself. But an overgeneralization, SO is on, S3 is sleeping, S4 is hibernate, and S5 should be off. Now, in order to get to the next state, you have to get all the power rails from the previous state. So, for example, S5 is off. All the power rails that are supposed to be present when the computer is off in S5 have to be present for it to hibernate. All the power rails present for it to hibernate have to be present for it to sleep. All the power rails present when it's sleep have to be present for it to be on. Make sense? So, for example, an S3 power line may be a line for the memory because the memory has to be on when it's sleeping, because when you close the lid and you choose to go to sleep, that's where it's going to store all your open applications in RAM. If you hibernate, again, I'm going outside of what I know about here, I believe when you hibernate that it sends everything over to the hard drive or the solid state drive rather than keeping it in memory. So hibernate, I believe, is where the RAM is even going to get turned off. So, and the SO rails are rails like CPU and rails like backlight. You don't need the backlight to be on when the computer is sleeping. So that's an SO rail. You don't need the CPU to be on when the computer is hibernating. That's why the CPU power is going to be, or the fan is all on the SO rails. So when you look at a list like this of all the different rails, you're going to see a list of rails. Here we go. So we have G3 hot. A G3 hot rail means it should be there all the time. So PP bus should be there all the time. PP DC in, the DC in rail should be there all the time. If we continue scrolling down here, the RTC rail should be there all the time. PP5 ES5 should be there when it's off. S4 when it's hibernating, SO when it's on. So if even one of these rails, one of these SO rails is present, what that tells me is that I can ignore checking every single S5, S3, and S4 rail. So all these things that say S3, S3, S5, I can ignore those and just focus on the SO. So it's a quick method of process of elimination. Once I see that the SO rails are the rails that are... Once I see that the SO rails are present, even one of them is present, I know that I now don't have to check the S4 or the S3s or any of those. And it saves me a lot of time. So now I can focus on which SO is going to be missing. And again, I can also now continue with my context. So now I've put this into context. I know what's going on with it. I know that there was probably liquid over here. Somebody watched the video that I did on removing the connector to fix the board, because I did do a video on that a while ago, but they left a little bit of solder there. Now, even though this section of the board looks clean, it looks like it was soldered over by somebody, even though that section is clean, now I know that that's my hint that water went there. So now I'm a detective. And then when I thought to myself, okay, water went there, that's how I knew to replace these termination resistors by the BIOS. I mean the SPI ROM chip, for those of you who will get angry at me. And now I know that water went there, so now that I know water went here and I did that and nothing's working, what do I do next? What is next? Right under it. Because this is the area right under it. Again, when you're on the trail, when the detective is on the trail, he doesn't like go, ha, I'm finding it, aha, I'm getting somewhere, yes, yes. And then when he's out of hinge, just decides to go all the way back here. No, he stops on the trail, whatever step he's in, and then while he's over here, he's like, dust for fingerprints, look around, what's going on, do I hear anything? They don't just go all the way back to the bottom, they continue investigating where they were, and that's the exact same thing that we're going to do here. Now, we look over here, this looks like shit. See this over here? See, when you can see the white end of a resistor, when you can see that white stuff, you're screwed. So for example, if I want to point out something that looks like the way it's supposed to, let's take this component right here. You can still see that it has these metal ends. You see the metal ends? And by the way, if you guys wonder why I don't buy the articulating microscope stand, do you see how steady that is even if I start moving around a lot? when you have the articulating stand, you can't really move around or even just look into it because it's constantly shaking. So the reason I like this boom stand that I have is because it's very, very sturdy, even if it means I have to, it's a pain in the ass to move around. Anyway, so that's a good one. You can clearly see the ends of the component, whereas here you don't. It looks like balls. This is just balls. So let's take a look at that, because when I say it looks like balls, what I'm talking about is this is no longer the metal end. I can see this like white styrofoamish looking substance, and when you scratch at it, it just doesn't feel like metal anymore. Now, when I look at the board view software, if I look at the board view software and I click on it, it's going to say that this is R7425. So let's look up R7425. And R7425 is supposed to be a 0 ohm resistor. So this is part of a resistor capacitor that is going to here we go. So this line going out here. So this is supposed to be 1.2 volts for an S3 rail. That's interesting. That's interesting that that's an S3 rail, because as I said, I should be getting the S3 rails if I'm already in SOs. Huh. Well, something interesting is going on here. Something very interesting is going on here. So let's see. Let's find that signal. Okay, so that is going to power RAM. Let's just find that component. Okay. R7450. R7450. I'll be able to measure that in R7450. R7450. Now, if I go to R7450, which is going to be right by the solid-state drive, I should be able to measure the 1.2 volts. So let's take a look at that in the microscope. That doesn't look too terrible, so I'm going to plug this in and see if I get 1.2 volts there. And if I do, that'll mean that my trail is starting to go cold. So I'm hoping that I don't get 1.2 volts. I just plugged everything in, and I'm getting 0 volts there. So that's really interesting. What interests me is that I was able to get 5 volts on an SO rail, but I'm getting nothing on this one. That's really, really interesting, because I've never seen a case in the past where I had an S3 rail without having an SO one. I mean, it's obvious why for the usual rail. So, for example, like PP5ES3 literally becomes PP5ESO. So that 0 ohm resistor is giving me an open line here. So that 0 ohm resistor is destroyed. So in the case of a standard rail like let's see, power, FET, page 58, here we go. Yeah, so for example, PP3V3S5 becomes PP3V3S4. PP3V3S5 also becomes PP3V3S3. So I'm not really used to one being present without the other. I guess here you could actually technically get to an SO without even being an S3. Can you even? I don't know. It's getting kind of confusing. I guess that there is no... I'm guessing that there is no power good signal. I don't think there is a power good signal that ensures that this is present before you go to SO. Maybe that's been taken away. Because usually, if you're not in an S3 state, you really can't... all your S3s are not present in the older machines, you're not getting to SO. I guess the newer MacBook Air is designed a little bit differently. They don't really care. They figure if you're in an SO state before you've gotten S3, that your computer is fucked, and it doesn't really matter for power-saving reasons anyway. Because they know that that circuitry is only going to save your computer power if it's totally destroyed, in which case power savings is probably not important to you. Anyway, let's stop blabbering and get on to replacing that little resistor. That really fucking sucks, because I used to like that method of troubleshooting. That sucks. I mean, I know what's wrong with the board now, but still, it doesn't take away the fact that that sucks. So there's nothing on here to check. That signal is not part of any P-good circuit. Lame. Lame, 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 lame. I mean, I know it's going to work now, but still lame. Doesn't matter how much you think you know, the shit is always changing. So I saw something that looked really nasty there, which is why I did that. And now, gonna get all the lead-free solder sucked up into my solder ball. It's my favorite. Goodbye, lead-free. Okay. Now to place my resistor. Ah, drat. Okay, how much more treachery will this board give me? Alright, so we're going to continue on the scent. Remember what I said. The good detective is going to look around. So what do I get on that power rail now? I still got 0. Okay, so what's going to... So now I'm still going to look in this area. I'm still on the scent. I'm on the scent. I'm going to stay over here. Stay in this area. My problem is still probably related to something in that area. Turn off the air filter because after I got my earwax removed, that thing is going to make me deaf. Okay, so we've already kind of fixed the things that looked nasty. Now, and there's still more that looks nasty. Okay, so let's see. Are we getting voltage into this IC? So I should have PP5ES5 at pin 12. So let's look up where pin 12 is going to be. Pin 12 is going to be... Where am I? Ah, here we are. Pin 12 is U. So I should have 5 volts at pin 12. Which I do, even though that looks kind of like balls. Right over here. Okay. Now I need to see what I have on pin 17 and 16. Those are the enables. If I don't have voltage on the enables, this will be painful. And somehow it decided to turn itself on. I think me scratching actually did something. I don't know if you saw that or not because I was on the camera, but I started scratching at this thing and it turned on. So what I'm going to do now is I'm just going to scratch the rest of it. Don't argue with what works. Make a nice looking connection there. This cap looks like dog shit, so that's just got to go. Let's see. Do I have the patience to wait for the hot air to turn on, or am I going to try to turn it off with my take it out with my soldering iron? We got it. I don't have the patience for the wait for the hot air. And I'll take this one too. That looks nasty as hell. All right. Yoink. Okay. Now it's a little bit of cleanup. We're back to factory. You people with really good hands are probably laughing at me. Good enough. Yeah, this is that looks like shit. I'm not gonna trust this to stay together. Right, so let's see. What can we do here? When I say it looks like shit, I mean the path where 5 volts is gonna come to the chip. No. I don't feel like having this come back for warranty a day after I give it back to the customer. Okay, so we go like this. It's going to tin the ends of the wire a little bit. This is no fun when you're me. Okay, get the tiny iron on. Beep, you schmuck. This. And should I offer this? Okay, now down here. Okay, much better. This is something I can actually trust will last and not just fall apart. And yeah, good measure. That's a good strong wire there. Now look at that fan spin. It's beautiful. So that's that, another board working, and as always with these videos, I hope you learned something.